All right. Cool. Yeah.
We did accidentally use the ratio test, but we still have to set for like absolute.
No. Ratio test does absolute. Yeah. It would just be. I don't know. I didn't really think about this problem if it would be that much harder, but normally it is.
That's the one we did in your office.
Yeah, that would be disgusting. Because you'd have to. It's very similar to the one where I asked you to prove the limit was e or 1 over e. Because you get something that doesn't. You get n plus something to the nth power over n plus something to the nth power, and that limit. Yeah, so the ratio test there would lead to that kind of thing, which would, open the door to a lot more difficult stuff that you don't have to worry about if you just do the root test. Yeah. Now you might notice on number 3, I wanted to make some really neat series, so I constructed that series without any consideration to how difficult the endpoints would become. And I started doing the endpoint, I'm like, no, I don't want to do that. So that would be one if they gave you that one. I'd say, don't worry about the endpoints like it did on the quiz. Because here, you'd have to understand a lot more about how factorials interact, right? You can't even take a limit of a factorial very easily. L'Hopital's doesn't know what to do with it because what's the derivative of a factorial? It's not you bring the factorial down and make it a question mark. No, it doesn't work that way. So I didn't mean to. I wasn't even thinking about what the endpoints would look like, and they ended up looking like remarkably disgusting. So for that one, I would just want you to do the body of it and not worry about the endpoints. Something like number 6, you should expect that I'm going to make you graph that yourself. On the practice final, I gave you the picture, right? It's sort of like the fish we did on the quiz. I'd give you a problem like that. You have to graph it yourself. And then I might ask you calculus-related questions on it. So, just to really make it clear, the trig stuff, just going way back, just kind of addressing what it is you need to know. Obviously, the trig stuff on the handout above the black line, you still have to know that, right? If I ask you for anything else, I'll give it to you. I'm going to give you Taylor series definition, just like it did on the quiz. What else, Jeff? If I ask you something about the polar derivatives, I'll give you that formula because you mess up one place in there and the whole thing goes to hell. You with me? The whole dr, cosine theta, all that kind of business. The parametric one you got to know because it's really damn easy, right? The polar one, it's not as easy, so I'll give you that one if I ask you something about that. Yeah.
The parametric one you're supposed to know?
Yes.
What's that?
Oh, which one is that? How do you find dy dx for parametrically defined? Yeah, you just got to chuck in there a dt, right? Bam! And then the polar is like a few more steps, and you get this monster. Yeah.
Going to from the quiz on number 2, when we're trying to get y by itself by taking the root, not the square root, do you flip it?
So on the one that had the square on the t, is that what you're looking at?
I'm looking at the one that is the cube root or the
Oh.
square root of cube.
Okay, all right.
I brought it up and then
Oh yeah. So there was no way to do it without just doing it.
Yeah.
So if I've got this, so some of you guys had this, and some of you guys had 1 over ln of t. Right, which is a lot easier in a sense, but not really. The first thing I would do is rewrite this as t to a power.
Yeah.
And that's where a lot of us screwed up. Some of us thought there was a cube root in there, and there isn't. Right? So some of us didn't know where the 3 went. So this is a little, kind of thing is a little troubling, but on the bottom of plants there are roots, right? So on the bottom goes the root, and what's the root? 2. And the power's 3, and it's flipped so it's negative. Now the next question becomes, how do you solve for t? It's nowhere near as hard as you might think it is. Yeah, but you could do 2 things at once. It's sort of like solving this equation. How would you solve this equation in 1 step? Multiply by the reciprocal, right? So here, I would raise to the reciprocal. Yeah, so square and cube root at the same time. So you get t equals y to the negative 2/3, and you can throw that in the other dude. Be sure to simplify it a little bit. If you have ln of that, can't the negative 2/3? Yeah, there you go. Cool. So do at least a little bit of simplification if there's something sitting there. Here's something about whenever you create a Taylor polynomial, you almost always should be able to write the coefficients as at least fractions. You should, I mean, if you have to go to decimals and truncate, that sort of takes away from the whole idea. If every single one of your terms in your Taylor polynomial is somehow rounded, you've lost the idea of what you're trying to. Then it's not a question about how many places to go out because you're screwed from the beginning. So you want every one of them to be exact. And then you control how close you get by how many terms you go out. Not by how much you round something. You don't want to round it at all. And you have control, in general, in the real world, you have control over what you pick a to be. So if I'm trying to do something for the 5th root, I'm not going to pick a to be 22. That sucks. 5th root of 22 is 9. I would pick it to be 32 maybe, because the 5th root of 32 is 2. Yay. So that choice is going to make all of my coefficients nice. Or, you know, what nice means for us at Calculus 2 level, which is a fraction that might be 212 over 4,947. That is still nice. Believe it or not. So when I ask you for Taylor polynomial, just make sure that you can write it in general, and all your coefficients should be fractions. They should be based off of something fundamentally easy to do. The next level of that, look at number 5 on the practice final. I'm doing the function 1 over square root of 2x plus 1. Right, so I mean, when if I'm about to do my Taylor, I would write it, of course, like that. So then I'm going to attack it with derivatives easy. But once you do all that, and I'm asking you to figure out what 1 over the square root of 8.8 is, bless you. Of course, the way I'm about to ask this question, I'm going to give it away. But would I just plug 8.8 in to my Taylor polynomial? Hell no, right? Well, how do I figure out what I plug in then? Yeah, I'm saying when does 2x plus 1, when does that equal 8.8? Solve it. That'll tell you what value has to be plugged in for x to make the result the question that I'm asking you, right? So be really careful about, on the quiz I was really nice, because I wrote it as f of, and I gave you what x was. On the final, I'm not going to do that. I'm going to say this, and you have to take a second to figure out, okay, what x would make that happen? Cool. Yes, ma'am. Oh, yeah. If you've taken, again, I think a few of you guys have taken statistics before. 4B is directly related to the z-score chart and actually doing the calculus to fill it in. So this gives you the area under a normal curve from 0 to 1 as z-scores. If you've never taken stats, everything I just said doesn't make any sense. So, but it's just integrate that. So, part A, you've got to, of course, figure out what that looks like. And the nice thing is, again, I told you I'd give you that table from the book with all the different Taylor series written for each function that we know. So, like e to the x, sine x, cosine x, all those kind of stuff. But then I'll ask you a question like this. Okay, now make a new function based off of that. So all I got to do for this part A is do what? Yeah, plug in negative 1/2 x squared into x, right? Just so I can piggyback up what I've already done. You get this here. So that's what you get when you just plug in negative 1/2 x squared, plug that into the definition of e to the x. And then I ask you in part B, I ask you to integrate this so now you just got to plug those terms in. And now integration is relatively easy because it's just a polynomial, right? And I tried to show, I think, or did I? No. I thought I did that somewhere. I guess not. Oh yeah, I threw in the extra term and then I found out that it wasn't needed because it didn't change the decimal place I wanted at the end. So here you got, I don't know, where did this stop making sense, or did it make sense at any point? Or did you ask the question?
Yeah, I'm good now.
Oh, okay.
I was having trouble connecting it to the video. Oh, yeah.
Yeah.
Then just pull the integral sign, like, individually.
Exactly. Yeah, now you got individual terms. We know we can integrate each piece separately. The nice thing is you end up with everything's got x, so the 0 part doesn't really throw anything off. So I don't know if you guys remember, anybody in stats, and you know, the fact that it's a 2 doubles this, so it actually is from negative 1 to 1. So if you've taken stats, what percentage roughly is from negative 1 to 1 standard deviation, within 1 standard deviation of the mean? In a normal curve, there's almost 68%. Is that, if you've taken stats, it's in the brain somewhere. And sure enough, that's what I got, 68.2 blah blah. You really should take stats. It's remarkably useful.
Is it 4 units now?
Huh?
The stats 4 units now?
It is. Finally, thank God. We can finally fit everything in. Shot.
So for that one problem with number 5, you told us we had to figure out how x equals the number. Can you show us how we, I don't know if you already did that, can you show us how we can do that?
Yeah, so I Let's see, what did I do? Oh yeah, I just said it's 3.9. So for that one, you take, I know the function definition is 1 over square root of 2x plus 1. My question is what's 1 over square root of 8.8, so then you just got to say, okay, what x makes it become 8.8? Subtract 1,
Okay, so just solve for it.
divide by 2, that's where I get the 3.9.
Okay.
Yep.
So how much of the final is going to be from like the beginning of the semester? Like,
I have no idea. I mean, not a ton.
yeah.
I mean, it's sort of going to be almost the same percentages here. You know I'm going to give you some stuff from that first chapter. You know you're going to get it by parts.
Are we going to get a lot of like trig slips and stuff like that?
Not a ton. I would maybe give you one like I did on the practice final. You know you're going to get at least one trig sub just to, I can make sure that you can do it. At least one by parts. You know you're probably going to get something related to a u sub. 1c you could use u sub, but you really shouldn't need to anymore, right? The inside's 2x, you just got to take care of that 2 in the right way. Does that make sense if I say that? Okay. Yeah, so I have a quick little thing, maybe with at most one problem from each section of Chapter 7 representing Chapter 7, right? Yeah. Which one? 8C? So if I ask you to convert from rectangular to polar, or Cartesian to polar, however I want to say it, what would you do with this? What's x in polar speak? R cosine theta? Y is? And then I just do the same thing here, right? Just multiply them. So what I did is to simplify it a little bit. One R can die on both sides, right? And then I can solve for R. You know, if you get an R squared, don't solve for R. Don't bring plus and minus into it. But if I kill an R everywhere, then I get R equals, and I can divide by cosine sine. And then I just went further. You could stop there, but you could go further because the cosine would cancel. If you broke this up, and you get 1 over sine, which is cosecant. Yeah, so that's where I went for the last step.
Are you gonna do something like that and then have this like graph of 0.25 or something like that?
It's possible.
I think that's evil.
No, it's not evil. I do that to my pre-calc students.
Yeah.
I give them something in polar and make them change it, and then it comes out to be a hyperbola that's been shifted, so they have to complete the square to figure out the center and blah, blah, blah. Huh? If I had... What would I put there? So say I was solving this equation. How do you complete the square? Good. Half of 8 is 4. Squared is 16. So then I would get x minus 4. This always factors as the first step. Half of negative 8 is negative 4. Yeah, and then you can square root and go from there, right? So that process is used to put circles, hyperbolas, ellipses, to put them into standard form. Yeah?
If you give us something for like Simpson's rule or trapezoid rule, do you want us to have those equations memorized? Or
I'm not. You might notice I even left it off of the... Yeah, the funny thing is, I want you to realize that those... What's important with those is the idea that goes into producing their formulas. But the minute you've produced the formula, it should be easy. Because now it's just plug and chuck. So that's why you might hope I put one on there with it, but I'm not. It's good to know they exist, and you actually use them all the damn time in engineering, in all kinds of fields where you just need a quick approximation for something. You use Simpson's rule is used a lot. In fact, you have to know it to pass one of the engineering exams, I think, or something. Can't remember off the top of my head now. I was looking that up sometime. Just so I can know. I don't want to be an engineer. Sorry. It's not for me. But it could be for you. You can make a good amount of money. Oh. Okay. Facing the wrong way. By the way, I think it was this class that didn't film last time. The video was not there. So, were you guys looking for that?
What were you saying?
Yeah. So my front row guys, you got to tell me if it's. I don't know what happened to the poor little dude.
I could have sworn it was on and then it turned off.
Okay. It decided, took a union break. I don't know. He just gets union breaks random times. So it was like this here, right?
Yeah.
Should be 2 probably. I think it's when I changed it to.
Maybe that's one.
And the question here was, does this thing converge or diverge, or what's it do, right? So, yeah, if it's convergent. So, I mean, what do you always try first if you're not sure? I mean, can you tell if that's going to converge or diverge?
Test for divergence.
Test for divergence. I love it. And to do the test for divergence, what do you have to do? What is that? Show that the limit is not 0. I like it. So what kind of sucks about trying to do this limit? It looks like it's going to be disgusting. In fact, the way it's written, it's impossible, basically.
Break it up, though, can't you?
Yeah, then you get indeterminate form, right? You get infinity minus infinity, which is not 0.
Can't do a little multiple against.
Not yet.
Is this?
But that's the trick. You always, if you can't tell and it's an indeterminate form, you try to write it how? So you can use L'Hopital's.
Yeah, make that 2n minus 1 over n minus 1.
Beautiful. Use the property laws. So, Jordan, man. All right. So sort of like, remember that the one that we all loved a lot where I had you guys try to show it was e or 1 over e? So you had to take n times that and make it 1 over n under the bottom. You always try to make it a ratio somehow. With logs, you just apply the property logs. So this will be ln. Now your next question might be, well, it still doesn't help me out because now it's the limit of an ln, but what can I do with the limit? Because ln is continuous. And of course, what's the limit at inside thing going to be now? 2. So the limit of this is ln of 2, which is not. So this thing diverges. Cool.
Finally, probably give us a conceptual question on Taylor series, probably like the ones you did in the past. How would you approach one of those like ratio? Would you have to use one of the ratio tests?
I'll tell you what is not a bad idea to at least look at the homework at the near to the end in the Taylor polynomial section and just see, that's where the conceptual questions sort of always live, right? So if you look at section 1110, with some good ones. I like it. There's not a ton in here.
Number 4 was like that. They had us do a ratio test to try to solve that.
Oh yeah, number 4 is good. Number 4 is so easy that it's you can't tell it's easy. The way they've written it is like, holy shit, what do I do with this? But what does a Taylor polynomial look like? It looks like the nth derivative of f evaluated at some number over n factorial. I like it. So that's the basic form of it, right? So do you see how if they tell me what fn of 4 is, that means a is 4, and they're giving me what that thing is? They're telling me exactly, you just plug that thing there. And then you can attack that with ratio test or root test or whatever makes sense. Yeah. So it's almost too easy. It's like you don't have to do anything with this. They tell you that the nth derivative of f at 4 is, where'd it go, Jeff? There it is. You don't know what f is, but you don't care. So when you plug that in, what's the nice thing that's going to happen there? What's one nice thing? The n factorial is going to go away. So then f of x in Taylor polynomial form would look like, what do I have? Comes here. Would look like -1 to the n factorial cancels over 3 to the n plus 1 times x minus a, and what's a? 4. Now just attack that with ratio test. Could you attack that with root test? It wouldn't be very easy because that would be like n plus 1 to the 1 over nth power. So it might not be a great way to go. Well, you can still do it. It'll still work. But it just looks weird. The information they give you looks weird. But you got to realize they're giving you this piece of the coefficients. And they just got to plug what they tell you. They get, oh, sweet. And the n factorial cancel, it kicks ass. So they basically put it together for you. Because what's the first thing we do when we try to make a Taylor series for something? What do? What's the first couple steps? Make a list of the derivatives. Make a list of the function and the derivatives evaluated at A. Well, they did that for us. They already did that for us. In fact, they got the list and they figured out the pattern in the damn thing. Oh, man, they did like 75% of the work. So we just got to plug it in. Kicks ass. Yeah.
I have a stupid question when it comes to finding.
Cool.
So you know how, like on the quiz, for example, the equation that we're using was 9x raised to the 1/3, and then it's evaluated around the derivative. When I'm finding the derivatives, so I have, like, say my first derivative is 3 times 9x raised to the -2/3. Do I plug in that 3 with the 9x, or do I just leave it out by itself?
Well, the first step is to get the derivative, and the second step is to put 3 into each one of those derivatives, right? Yeah. So eventually you're going to put a 3 in there. Right. The thing to realize is, like I said earlier, I'm always going to build a Taylor series around an easy to evaluate value, right? So if it is 9x to the 1/3, and the biggest mistake I saw was people just took this out, which completely changed the function. Now you're doing a different problem. It's not the problem I asked you. And of course the derivative is going to involve chain rule, right? Yeah. So then you do get 3.
Do you
But
plug that? My question is, do you put that 3 with the 9? Or is that still?
Well, the next thing you do is f prime of 3, right? That's the next thing you do. Once you get all the derivatives, you plug a into them, right?
Yeah, I got you.
And just realize, of course, when you plug a 3 in, what do you get? 27 to the 1/3 is 3. And then this is 3 to the -2, right? And then you're going to get 3 to the -5th, and you're going to get 3 to the -8.
So
I don't know if you guys see that. That's what I meant earlier by you should be able to write all of your coefficients as nice fractions, because at the heart of them, they should be an easy to evaluate number, or else the whole idea is not, something weird. It should be easy to evaluate, and then I want to go a little bit away from there and see if I can come up with a function that would approximate it well. That's the whole idea. Why would I start with an ugly thing, trying to approximate ugly things? Doesn't make any sense. Yeah. Okay, so this is the one I was talking about. I would give you the formula for dr stuff, the dy dx, in terms of polar. So it's dr d theta. Let's see if I remember it. I think that's it. Let's see if I'm right. Is it? Cool. So either I'm right twice or I'm wrong twice. Here it is. So this is the polar equivalent to dy dt dx dt. So it's a little bit more complicated. But I give you r is 4 sine 3 theta. So now you just kind of start evaluating the pieces parts and then you put them all together. That to me is the way that makes the most sense. So what's dr d theta? Yeah, chain rule, 12 cosine 3 theta. So that's going to go here and here. And then the rest of it is given to you. And then you just got to plug in pi over 3, right? Is that cool? Huh? Well, I did already. It's right here. Does that make sense? So yeah, just plug this here and here. Plug in pi over 3 for theta, and just see what you get. What goes here? And here? 4 sine 3 theta, because that's what r is. Good. And of course, when you plug in pi over 3, what do you get here? 3 times pi over 3 is pi. Sine of pi is 0. So, I mean, that part's going to go to 0, right? So let those parts be easy. I think both of these end up canceling because they both have r in them, right? So when you plug in pi over 3, this is going to go to 0. This is going to go to 0. These are both going to be 12 times cosine of 3 times pi over 3. So cosine of pi is -1. So I get -12 and -12, and then I just figure out what sine of pi over 3 is. And cosine of pi over 3, and that's the answer. Yeah, it's just a bunch of plug and shove now. So I mean, that happens all the time in math, right? You especially in statistics. I know I keep bringing statistics up, but stats is really good for this. Crazy, weird-ass concept. Really weird. Takes like 2.5 classes to talk about the idea. And then what's it look like for you in the homework? Oh, you divide this thing by n, and that's it. Everything else is the same. I mean, so the concept is crazy, and it's like, oh, God. But once you got it, plug and shove. Right? You've already done the hard work, which was explaining why this works. And to use it should be easy. Did I ask for, no. I just asked for number 7, I just asked for the tangent line slope. But like 6a, I asked for the full equation of the tangent line. And that's the question you got to ask every now and again in calc. Once you learn derivatives, you're like, oh, we got whole new ways to figure out equations of tangent lines. See? Oh, yeah. Yummy. So what's so what? What's some stuff you can try? What sort of a giveaway in this problem is that seventh power? I can't possibly expect you to do that. So what does it feel like this probably must be eventually? Yeah, I have to use some trig identities, but eventually it's going to boil down to a u sub. Trig sub is when you start with x's and you replace them with trig functions, yeah. So I currently, if I let u equal this, it's not going to be that. If I let u equal that, it's not going to be this. So I got to do some work here.
Cosine 2x equals 2 sine cosine.
I will.
And then let u equals
Careful. Hold on. Cosine 2x, you're thinking sine 2x. What's cosine 2x's identity?
1 sine squared.
And maybe make it related to this somehow, a little bit.
Cosine squared minus.
Yeah, cosine squared minus sine squared. Did I talk to you guys a little bit about like cosine is an asshole? I mean,
Yeah.
cosine's a jerk. So cosine of 2x, he's first. Nah, cosine squared is first. Right, so you don't mix those up. Or whatever sticks in my head. That sticks in my head always. Cosine's an asshole. Yeah, I'm first, man. I really don't know what it's like. So how does this help me? If I obviously I'm going to have to let u equal what? U's got to equal what? It's got to be, yeah, this. I think that's what you guys are saying. You just sort of like fade out at the end. So if I let u equal that, does du equal this? No. But what's nice about this?
Plus minus.
Difference of squares. What is the derivative? Let's try it. If I let u equal to cosine x plus sine x, what's this derivative? Yeah, negative sine plus cosine. So like cosine minus sine, right? Do you see what I'm saying? I know this is probably going to be u sub because it's 7. I know then that this is going to have to be u. I might as well figure out what du has to be and see what I can do to make that show up. And sure enough, this guy's got that in it, and it's got another one of these in it. Yeah, because it's just a difference of squares. So the integral cosine x plus sine x to the 7th, cosine x plus sine x, cosine x minus sine x. This will be du, right? And now I've got 8 of these. So if I let u equal this, du is that, so I get u to the 8th du. Crazy. So that's the kind of way that trig identities could show up in a problem, right? So I'm not going to have this explicit do this trig identity section. That was nice. I like that. And one guy, his ringtone was brains. It's like in the middle of this silent, they were working on brains. I'm like, I watch too much Walking Dead, man. Don't be doing that. Like, it has started. It has started. I must go to my zombie fortress. It's okay, don't worry about it. We've already forgotten.
Did you see the mid-season finale?
Oh my God, dude! Yes. Stop. Did you see when they were the cast was at? You know, everybody's yeah. You saw Boondock Saints, right? That's why I love the fact that Norman Reedus is in there.
Oh, yeah.
Anyway, all right. Sorry. If you don't watch it, sorry. We'll stop talking about it. Oh yeah, so that's like number 1C on the practice final, right?
Yeah.
So remember that section where we talked about, so that's 1C on the practice final. It's that trig integral stuff. So it's not trig sub, it's just straight up trig integral. So you got that problem already. If I had something like, so I remember how to do this.
Take off on the secant.
All right, so you can shuck off one of the secants. And how does that help you? So just, yeah, if you let u equal tangent, then du would be secant squared, right? And then I have like an extra secant hanging out that I don't know what the hell to do with. If I had an extra couple secants, that would be awesome because I could rewrite it in terms of tangent then. Are you guys kind of... So I don't want to let u equal tangent. It's not going to work. So if I let u equal secant, which is kind of like what I think I heard you say, derivative of secant is tangent secant, right? So if I do that though, how many tangents do I have left? One. But I mean, that's the kind of things you start to think about I don't try to memorize this stuff. I try to attack it as it is. I can't let, if I try to let u equal secant, then du is tangent secant, and I have one tangent left. That sucks.
You turn them into cosine and sine.
Yeah, you can try that next, right? But then, I mean, it's then it becomes, what does it become? It becomes sine squared over cosine to the, right? And this will actually work, sort of, maybe. Will that work? Yeah, so up here, if this would have been a fourth power, it would have worked beautifully, right?
Oh, yeah.
But it didn't work that way.
Never does.
Yeah. Especially if you just make it up out of nowhere. Yeah.
Did you replace the sine squared with the, what was it, 1/2 minus cosine, or no, 1/2 minus, is it cosine 2x over 2?
Yeah, but then you have a problem with one of your cosines is x and the other one's 2x, so they don't play well together, right? So if I try to let u equal a cosine here, du would be one of these sines, but then there's like an extra sign.
Could you do something with like the tangent squared plus 1 secant squared?
Say what?
Tangent squared plus 1 secant squared.
That's what we want to use. So let's go back. So since I just made this up out of nowhere, I made one that's a little bit gross. If this was a fourth here, what could I do? So now there's two secants that can come off of here, and it leaves two secants. So if I take two secants off of this, that means I'm going to let u equal what? If I have two secants that can come over here with a dx, that would be du, so what would u be? Tangent. Right? So if I rewrite this as tan squared, secant squared, let u equal tangent, du is secant squared. So this is du, this is u squared. What do I do with this poor little dude?
Turn them into tangent.
Yeah, relate them back to tangent. Now be careful. Tangent squared plus 1 is secant squared. Cool. I love it. So now you get integral of u squared times u squared plus 1 times du. And then you can, that's easy. Yeah.
Tricky stuff. Now, would there have been a way to do it when secant was cubed instead of?
I don't know, I gotta think about it.
There's also things
I didn't mean to make it that gross.
There was something like 7-3. I don't see anything on it.
7-3. Oh yeah, trig sub, number 1.
Oh yeah.
Yeah. The very first one's trig sub. So the thing that a lot of people forgot on trig sub is at the very end, you don't want to end with theta. You got to always take it back to x, right? I can't believe it's December.
Right? Hot class. Can we do a trick sub?
Sure. I was going to say, time flies even if you're not having. Oh, let's see. If I make one up out of nowhere, it's probably going to be gross. Let's see. Let's try this one. Bless you. So I don't know if any of you guys think this way yet, but when I see something like this, my brain goes, can I write those as series? Do it that way, but maybe you're not there. I don't know. Maybe you're like, no, Jeff, I'm very happy. This is not a serious problem. So what tells me this has to be trig sub?
Perfect square of the square.
Yeah, it's because the derivative of this is not out here, right?
Yeah.
The derivative of this would be negative 2x, but there's too much out here. If that was just an x there, I wouldn't have to use trig sub, right? So be very careful if you're about to try to do trig sub. Make really sure it's not just a u sub. You're not making your troubles worse. Trig sub would work where u sub would work, but my God, I'd much rather do u. U sub is not going to work anyway here, so I got to do trig sub. What's my trig function that I want to use here? Yeah, because sine is like 1 minus sine squared is cosine. So I got constant minus function squared. That's the form I want to use for sine. What kind of sine?
4 sine.
4 sine. No, Jeff. There you go. And so dx would be 4 cosine. Easy. And that's the other part that people always left out, is you forgot that dx has to actually be replaced with an expression dealing with theta. So now you get, what goes here?
4 squared.
So now you get 16 minus dx, which is all this business here. What can I put out front of the integral? If I take all my numbers out. Yeah, 16, and I can take out of here square root of 16, which is 4, so I can put a 64 out there. And of course, I got to put my little parentheses around there, right? Those limits are good for x, not for theta.
Another 4 is here.
And another 4 down there, good. So that makes it 256. And then what am I left with in here? This will be eventually, if I take the 16 out, 1 minus sine squared is cosine squared. Square root is cosine times another cosine, and I got a sine there. So I get sine squared theta, cosine squared theta.
Wait.
Yeah.
What happened to the sine squared that was inside of the
So 1 minus sine squared is Square root of cosine squared is cosine times the other cosine is cosine squared. Cool. Now, I'm still getting way too many people that tell me this, and you know, this is the quickest way to make your calculus teacher cry. Actual tears just come. All right, so stop doing that. I'm joking and I'm not joking all at the same time. It's crazy. This is so desperately not true, right? This should be, I think I've said this to you before, it should be painful. It should hurt. I should have to force you to write this. And you go, I don't want to write it, Jeff, it's so wrong. Okay, I'll stop picking on you guys. But yeah. So what the hell, how do I do this?
Make one of them the other. So cosine, cosine, and cosine, cosine.
You have the 4 back and 2 sine 2x.
Yeah, so if I bring a 4 back in, but because it'll be 2 sine cosine squared, is that what you're thinking? That's one way you can try to go.
Sine 2x squared.
Exactly. So then you can consolidate it as sine 2x squared, which is still, it's better than where we are now. That's for damn sure, right? And we sort of get to the same place if I did like you're saying, wait, and I like replace cosine squared with 1 minus sine squared, so I get 1 minus sine to the 4th. But that way's a little bit better because then you get only a square, not a 4th power. Right? Do you see how does either one of these have an extra 1 to shuck off? If there was a sine cubed, I would let u equal cosine because I can take that sine over here. I don't have an extra 1 though. I don't have an extra 1 to put over there. All right. So I like the idea. It's a really cool idea. What he's saying is if you bring a factor of 4 back in, so I bring this back down to 64. Do you see how that's the square of 2 sine cosine? Right? Isn't that 2 sine cosine squared? And what's 2 sine theta cosine theta? Sine 2 theta. So you end up with
2 sine.
yeah, you end up with sine 2 theta squared. I don't need the parentheses with it.
Wouldn't it be 2 sine?
No, because each one gets a 2,
Oh,
right?
yeah.
That's why I brought that 4 back in. Yes, ma'am.
From there, couldn't you just do the 1/2 minus?
Good. So now you got sine squared. It's of 2 theta, but we don't care. Sine squared can be written as no. It's bouncing us around. We want to get away from squared. So 1 minus
Cosine 2x or 2 theta.
twice 2 theta, so 4 theta.
Over 2.
And now the integral is much easier, right? Do you guys see how we went from there to there? Now, to be honest, right here, you could do that for both of these and then just multiply those together. That's another way you could have done this whole thing. But I kind of like that suggestion about going that way. But it would work here. You can write this as 1 minus cosine 2 theta over 2, and this will be 1 plus cosine 2 theta over 2. You can multiply those out, right? Cool. But nobody suggested that, so I didn't do that. But here, the integral of 1/2 d theta is 1/2 theta, and the integral of negative cosine 4 theta over 2. Yeah, so negative sine 4 theta over 8. Good, because you got to have a factor of 4 that would kill the 4 that would want to come out of there, right? And then sort of from 0 to 4. Now I got to take it back to x, and then I can plug in my values for x. How do I transition back from theta to x? Oh, yeah.
Would it be a minus negative for the cosine sign or no?
No, because the derivative of sine is cosine, so I don't introduce a negative. If I was taking a derivative, then I would, yeah. So how do I go from theta back to x? Triangle. I like it. So from the very beginning, x is 4 sine theta, so sine theta is x over 4. So where does the x go?
Opposite.
Listen, that's SOHCAHTOA business. All right. And so now I just need to know, now sine of 4 theta, now here's the trade-off for doing it this way. To figure out sine of 4 theta, how am I going to do that? I really want you guys to understand, if this is theta, 4 theta is going to be some, it's going to be 4 times, I have to rewrite sine 4 theta in terms of trig functions of theta alone, right? So I'd actually have to, so this is one downfall. Here I don't have to take one step back. This is 2 theta. So I can write it in terms of theta in one step. Here I'd have to do, this is sine of twice 2 theta, which is 2 sine theta. Yeah. Then I have to rewrite each one of these in terms of theta. Do you guys see that? You can't just multiply an answer by 4. You can't do that because this is sine of a whole different angle. It's 4 times the angle I've got, but the ratios aren't necessarily related by 4. Does that make sense? You got to relate this back to theta, which is what you know everything about. Maybe. So, this ends up looking disgusting, but sine theta, cosine theta. Cosine 2 theta is cosine squared minus sine squared theta. Woo! And now I can just use this triangle to fill in all those because they're all based off of the angle that's in the triangle. Right? Yeah.
Should we expect something like this in the final?
No. Come on. I'm not going to do this to you, but I mean that should not be like a really by itself really difficult. It's more than you want it to be, but that doesn't make it difficult. It just makes it more than you wanted it to be, right? We should be able to rewrite sine 4 theta in terms of theta alone by applying the identities twice. So if I have sine 2 theta, how do I write it in terms of theta alone? 2 sine theta, cosine theta. So if I have sine 4 theta, the first step is 2 sine 2 theta, cosine 2 theta. And then I got to tackle each of those. I give as long as expression, but why do I not care? Because the values are very easy to get and just plug in. You're like, whatever you say. You're saying there's a chance that this might show up. No. All right. But again, the most important thing for you is to be able to identify what method to try from the beginning, because the way you're going to lose a lot of time is if you try the wrong method and get stuck somewhere. Yeah.
So the part that says 1/2 theta, and we just solve for theta in that case and plug it in.
Yeah, that's the inverse sine of x over 4, right?
So why can't we just solve for theta and plug it into the sine 4 theta?
So I'll give you this. If it's I always try to keep your identity skills sharp. But if it's an indefinite integral, even if you do that, you still have to do pretty much what we're doing right now. Because if I ask you to simplify this, so if theta is inverse sine of x over 4, right? So then sine of 4 theta, you might think, well, that's easy now. It's just sine of 4 sine inverse of x over. But what the hell's that mean? Right? So I'd still have to draw the triangle. I'd still have to do exactly what we're doing. But because it is a definite integral, so that just means I could just plug in, 4 and 1 into there and get my answers, right? Yeah. But you know me, I prefer indefinite because it kind of forces you to really take it all the way back. Yeah. Okay. Well, you're exactly right. If it's a definite integral, there are quicker ways to do it besides what we're doing. But if it's indefinite, we'd have to do something like this. Yeah.
So our test is only gonna be like 8 questions long, and little parts of the quiz are gonna be longer.
Let's see.
But it's more than part A.
Yeah, it's about 19 questions. Yeah, I
With the part A's.
in the low 20s of questions probably. So on the on the actual final, I'm going to have a few more problems that are very, very basic, right? Just the pure idea, and then I'll have some that are a little more challenging. Like I'll have number 3 is obviously a little more challenging with keeping track of everything. Right, but I might have a very simple, very, very stripped down version just to make sure you can apply the correct test in the correct way. But then I have to give you some more complicated ones to make sure that you can actually go through the whole problem and keep track of what's where and how to rewrite factorials and all that kind of business, right? So there will end up being like 22 or something questions on the final, but a decent little number of them will be quick hits, like there won't be sums loaded with stuff. It'll be very bare bones. But then expect me to also do, of course, you know me by now, I'm going to have stuff like number 3, number 4, I'm going to have stuff referencing that table of Taylor series. So I could ask you to do sine of, x squared plus 7. And you got to plug that into the series and do stuff and ask you to integrate it, right? Not a bad idea. Because if I try to integrate sine of x squared, not 7, that's good. If I try to integrate from 0 to 1 sine of x squared plus 1, can you do it? Can you do u sum?
No.
Would by parts help?
No.
Hell no, right? So this is exactly related to something like e to the x squared, which has been proven and shown. It's physically, totally, completely, mentally, every way, spiritually impossible to integrate. But now we can do it using series. A little trade-off, we have to stop somewhere and say, well, we can only be as close as the 15th decimal place, but for most humans, that's pretty damn good, right? So this would be one, I could write this in terms of sines Taylor series, put so many elements from it in here and integrate. Now it's a polynomial. It's easy as hell now, right? Just like that problem number 4 in the practice fund, where I use the E series. You're all like, I don't know what to expect, man. To me, the more useful thing I gave you is the study guide. I mean, to me, if I were you, I would just, if there's anything that I feel like I'd go do some problems out of that section, some odd ones, so I got the answers, and kind of check it off when I felt decently comfortable with it. This kind of is just a little checklist of, do you know how to do this? Do you know how to do this? Do you know how to do this? Yeah. Yeah. I sold it to you. All right. Sure. What's that? Sorry. That was funny. It's got me wondering about other teachers. Anyway, I'm going to stop wondering that. It'll make me sad. I don't know. I'll stop talking about it. Yes?
36 on 1110.
Oh, okay. So this is the x squared over. So here's an example of one they ask you to use a known series. So write a series for this. Section 1110, number 36. Yeah. So what known series in table 1, which is on page 762, looks like it might be related to that?
Binomial, right?
Yeah, good. Binomial. So if I write this, pull the x squared out of the way, how do I rewrite this to a power? Yeah, negative 1/2 power. Okay. So it looks like the binomial with k equal to negative 1/2. And the only thing is, it's 2 plus x, not 1 plus x, right? So how would I take care of that fact? What could I do? The more direct way to take care of it is you force a factor of 2 out of there, right? So if it would be a square root of 2, you take out on the bottom, right? So you can rewrite this as x squared over the square root of 2. So you pull its square root of 2 out. So what's going to be left now? 1 plus. So now I can just replace all the x's with x over 2 now, right? So the binomial. So I got this x squared over radical 2 that's sitting out there, right? It's not dependent on n. So it can totally just come in and out of the series that I'm going to write. This series would be 1 plus kx, so it'll be 1 minus 1/2 and x over 2. You guys with me? I'm just pulling it right off the table. This is the table I'm going to give you. And so this is exactly the kind of question I might ask. Blah, blah, blah. Plus negative 1/2 times negative 3/2 over 2 times x over 2 squared. I mean, we just plug and chug here now if you're following along with me. Page 762, I'm just putting negative 1/2 in for k. And I'm putting x over 2 in for x. Cool. You can go a few more times. And this asks you to do what? Okay. Cool. And if I wanted to write the... So this would be blah, 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 blah. If I wanted... And then I could bring an x squared in and a rad 2 in. But if I wanted to write the series for this... Let me show you. So the series is a little bit strange because it's got this piece to it here. Yeah, this is not k over n. This is actually combinatorics. This is k choose n. So if you've taken stats, you know what it is. If you haven't, then you don't. But have you ever seen Pascal's triangle? So each one of these, so this would be like 2 choose 0 is 1. How many ways can you choose 0 things from 2? One way, like this. I don't like either one. How many ways can you choose, I'm sorry, I said that wrong. No things from 2. How many ways can I choose one thing from 2? 2 ways, right? I can take the first thing or the second thing. All right, so we write this in stats, we write this as 2 choose 1. 2 things, choose one of them. So this is k choose n. So that's how they would get their coefficients. So it's really weird. What's really cool is this binomial series extends the idea of Pascal's triangle beyond integers, beyond whole numbers, right? We can now use fractions in there, which is weird. Oh, thank you. So if I wanted to write this series, it would be, oops, I left this out. Is that everything? Yeah. Sum n equals 0 to infinity, negative 1/2 n, and then just x to the n, so it'll be x over 2 to the n.
You can pull the x squared through, right?
Yeah, and then I can pull this x squared in. So now it'll be sum n equals 0 to infinity, negative 1/2 n, x. Let's write this as x to the n. So this would be x to the n plus 2, right?
Over 2n.
Over 2 to the n plus 1/2. Is that cool? Because we're bringing in 2 to the 1/2 power n. Freakiness. And then you can always compare. Do you get, if you plug in 0 and 1 and 2, do you get back each one of these sequence elements that you got? You can kind of double check to make sure it's right. So all they ask you to do there is get the series notation for that.
Question.
Yeah.
For the n choose k part, like with the fractions, I get it with the whole numbers because you got whole numbers. Like for n choose 1/2.
So the whole, let me see, it's been a while now since I've done this formula. Let me see if I remember. The formula for this is, let's see, you're getting into dangerous territory here, Joe. This sounds vaguely familiar, something like that, maybe. Oh, it's been too long. So you can kind of see the idea of repeated multiplication. You see that?
Yeah.
So it's really strange to think about. I want you to realize, I'm supposed to, for factorials, I'm supposed to keep going down to 1. But if I'm already negative, how does that work, right? But the nice thing with this is it kind of like chops off the tail end of it in a way. So I end up only worried about the first parts of it. I'm not sure I fully explain this. Maybe, oh, that's what it is. That's why this is looking weird to me. It's the other way around. So it chops off the tail end. So we only get the first whatever elements. So, how much time I got? So if I had 3 choose 2, that would be 3 factorial over 2 factorial times, oh, well, this is not exciting, 1 factorial. But if I had 7 choose 4, that would be 7 factorial over 4 factorial times 3 factorial. See how that would cut off the tail end of it right there?
Yeah.
So then you don't have to worry about, well, what is it? If it's supposed to go to 1, what would it go to if it's negative? You don't even worry about it because you just have to worry about the first few elements. And that's why the first few elements are what shows up here. And in the factorial piece, notice how there's no factorial in the general form? Because that's a part of this. That's kind of like related to the bottom here. Yeah, yeah, I wrote it right there. Good.
So it's fractions, it's just knowing that formula and then plug it in.
And the fact that it cuts the tail end off, because the problem with trying to plug a negative number, a negative fraction even, or any kind of fraction into a factorial is, it's supposed to keep going down by 1 until it gets to 1. So what the hell would that do? So if I just had this, that by itself, well, I'm not going to say it makes no sense, but it really, we'll just say it makes no sense. We'll just say that. But this, because of the fact that it cuts, and the problem with that is where does it stop, right? That kind of thing. But this cuts the tail end off. So you don't even have to know what the tail end is, because this cuts it off. Yeah, good. So that's an awesome question. But I loved it when I saw that, because I'm like, oh, now it's expanded the idea, at least in this very restrictive way. Only for these combinations, these combinatorics. Yeah. I think when they do the binomial for the first time, they explain some of this a little bit, but for us, it's just a plug and chug situation. I thought they did. Here it is. Yeah, page 761. Now, they actually don't talk much about it, do they? It's too bad for us. I don't know where the reference page. Oh, reference page 1 doesn't exist. Book. Rawr. Oh, there it is. There we go. So here's a nice representation. At the very front, just open the book. Don't go any pages. Binomial theorem. It's got it written out in a way where you can kind of maybe understand how fractions work in there. Cool. Okay. That's enough of that one. So I'm not going to get any deep stuff with the binomial theorem. I mean, it's a good question about why does it work the way it does, but the nice thing is it's just a plug and chug situation now, right? As always, if you guys are ready, we don't have to stay here. I don't know if you guys are afraid to leave or if you're worried someone's going to ask you a question and you want to know the answer to it. But if nobody has any questions, we're good.
So next time we meet is Thursday, right?
Yeah, this is Monday's the last day of classes in general. Tuesday, final start. So you have my schedule now for next week. Monday's my same office hours. So if you have to come see me Monday, same office hours. Thursday, and it starts at 11:35, so be careful. Our final starts at 11:35 on Thursday. If you come late, then I'm assuming you volunteered those half hour. You just didn't need it. I'm not staying late for you. I want to go and start grading immediately after that. Oh yeah, you gave it to me, right? Okay, that's my bad. I've got it. I didn't give it back.
No, not yet.
Okay.
10-1, 10-2.
You gave it to me. I just forgot to mark it. I was grading it, and then I forgot to mark that I had it because I haven't finished grading.
Homework 10-4 is not.
No, I made 10-4 extra credit.
Extra credit.
Yeah. Pretty sure I did, right? Yeah, I did.
No, 11 I think was extra credit.
No, 10-4 I made extra credit too. Yep. No, I'm probably not going to focus on that. But it just, it's good to know it exists. Especially going into Calc 3, you do end up doing a little bit of stuff. You do this kind of stuff now in 3 dimensions in Calc 3. Yeah. Thank you.
So 10-4 is in the test?
Say again?
10-4 is included.